We're going to calculate and compare Q values and predict the relative amounts of reactants and products based on equilibrium constant K. So we're going to look at both K and Q. We use K when we know we are at equilibrium, and we use the value Q when we are questioning if we're at equilibrium. So if we're given a set of conditions, a set of concentrations, and we're asked to determine whether or not we're at equilibrium, we calculate Q and we compare the value of Q to the given value of K to determine whether or not a system is at chemical equilibrium or not. Q is also called the reaction quotient, and this is what determines if a system is at equilibrium. We calculate Q the exact same way that we would calculate K. It's the same equation, the products over reactants, using the coefficients or the numbers that precede the substance as the powers. Just like with K, we can add or remove terms based on the number of reactants and products present in the reaction. We use this if we don't know if we are at equilibrium. Once we've determined the value of Q, and we can compare that to the value of K to figure out if a system is at equilibrium or not, and if not, which way the reaction is going to proceed to reach chemical equilibrium. Let's look at the first example of Q equals K. So when Q equals K, it tells us that our system is at equilibrium, which means that if its Q is less than K or Q is greater than K, we are not at equilibrium. And remember, our reaction tells us something about the concentration of products over the concentration of reactants. So if we have a scenario where Q is less than K, such as Q being equal to 2/3 and K being equal to 3/2, we see that Q is less than K, so we know we're not at equilibrium, but we want to figure out which way the reaction is going to proceed or favor in order to reach equilibrium. When Q is less than K, we are going to favor the forward reaction, which means we're going to make more products in order to reach equilibrium. In that case, the amount of products will increase, so the numerator increases, and the denominator, or the amount of reactants, will decrease. Whenever Q is less than K, we're going to favor the forward reaction. We're going to make more products and use up some of the reactants. This will increase the value of Q until it is equal to K, at which point we are at equilibrium. Next, we're going to look at an example where Q is greater than K. So for Q equal to 4/3 and K equal to 3/4, we see that our numerator is too large, our denominator is too small. So in order to get from Q to K to be at equilibrium, which is where every system wants to be, we need to favor the reverse reaction. When we favor the reverse reaction, we see we're going to increase the amount of reactants, which is in the denominator, and we are going to decrease the amount of products, which is in the numerator. This will reduce the value of Q until it's equal to K, and we are back at chemical equilibrium. Reactions will proceed in order to reach chemical equilibrium on their own. That ratio is where the system is happy.